Let's do an interesting calculation. This is about finding displacement when velocity varies. Let's say we have a car starting from rest, moving along a straight line, accelerating at 1 meter per second squared, and our interest is to find the displacement of the body during the second 10-second interval. That is, it's 10 seconds here, and say duration from 10 seconds to 20 seconds. The velocity would have increased. This is 10 meter per second. Velocity is increasing at the rate of 1 meter per second every second. So this is 20 meter per second. So this is our, well, we don't have a formula for varying velocity. If velocity were constant, displacement is velocity into time. So what we're going to do is improvise. Let's say we divide this 10-second duration into number of intervals and do a calculation like this. The displacement is sum of a special kind of a summation we'll do. Say we'll divide this 10-second duration into number of intervals and find the velocity for each interval, and then we'll add up the displacement for all the intervals. That way we would have taken care of the variation a little better. Instead of saying it is not varying, and instead of saying that we don't have a formula for varying velocity, we are doing something like this. Let's start off with, say, dividing this into 10 intervals of 1 second each. What is the velocity for the first interval? It varies from 10 meter per second to 11 meter per second, isn't it? It increases by 1 meter per second every second. So we'll take it as 10 meter per second for the first 1 second duration. So the displacement calculated this way will be 10 meter per second. It's varying, mind you, but we're treating it as constant at 10 meter per second. This is the duration. Then it's 11 meter per second into, again, 1 second. This goes on, and for the 10th interval, the velocity increases from 19 meter per second to 20 meter per second. So if you sum this up, you will get 145 meter. And we'll go the other way now. Let's say we'll take the velocity as constant at the higher end, higher of the values. So like say if it increased from 10 to 11 meter per second, let's treat it as constant 11 meter per second. So this will be the displacement for the first interval. Then for the second, it increased from 12 to 13, so we'll take it as 11 to 12, we take it as 12, plus so on and so forth. The last interval, it will increase from 19 to 20, we'll take it as 20 meter per second, and this will give you 155 meter. We could have kind of say the displacement yes is 150 plus or minus 5 meter. Now if you can make this a very small quantity, that will be a better calculation, and that's what we're going to do. What we've done is a continuous variation is being treated as a stepwise variation. We're going to increase the number of steps and make the calculation better. Let's say we'll divide this into 100 intervals of 0.1 second each. In the first 0.1 second, the velocity increases from 10 meter per second to 10.1 meter per second. So let's take it as 10 into 0.1. Then the second term will be 10.1. The velocity increases from 10.1 to 10.2. Let's take it as constant 10.1. And in the last second, this increase from 19.9 to 20. We'll take it as 19.9. And this will give us 149.5 meter. And if you do the other calculation like we did for S2, that is treat the velocity as constant at the higher end, it increased from 10 to 10.1 in the first 0.1 second interval, and well, it's taken as constant at 10.1. and if you go on doing this, the last second it increased from 19.9 to 20. Let's take it as constant 20, and if you do this calculation, you'll get 150.5 meter. That is, now we're going to write yes is 150 plus or minus 0.5 meter. Seems way better, right? But what is to stop us from dividing it to 1000 intervals, 10,000 intervals? In fact, we can increase the number of intervals, well, indefinitely, and increase the accuracy of calculation. Basically, this part will become smaller and smaller, and we'll be able to confidently say the displacement is 150 meter plus something so trivial that we will not bother. So displacement is 150 meter. Let's generalize this. Let's not define the number of intervals and start calculation for some capital N intervals. Say the calculation will go like this. S would be, for the first interval, let's say the velocity is v1, that into delta t. This delta t is, well, that we divide this t, total time t of 10 seconds into n intervals, so t by n, that will be delta t. So this is v1 delta t, plus the velocity increases by a delta t in the interval of delta t, right? It increases by, let's say this a is 1 meter per second squared here, but let's put it as it is, a delta t. Plus, if you go on, the velocity will be v1 plus a into n minus 1 delta t into delta t. Sorry, there should be delta t here. This is the sum, well, of n terms. Let's not bother about whether v1 is the velocity at the beginning of the interval or at the end of the interval. We'll show that it is irrelevant actually. This will be n times v1 delta t plus, this is a delta t squared plus 2a delta t squared. So a delta t squared comes out common into 1 plus 2 plus n minus 1. So this is the sum we got, and well, this n delta t is t, right? N delta t is t, v1 t plus this a delta t squared into sum of these terms is n into n minus 1 by 2. This is, after all, an arithmetic progression, and this will give us what? v1 t plus a, let's say delta t is what? T by n, isn't it? This is a t squared by n squared, a by 2 here, t squared by n squared. We'll put it this way, n into n minus 1, that is n squared minus n by n squared, right? And this will be what? v1 t, and this will be, well, n squared goes off and minus 1 by n, so 8 squared by 2 into 1 minus 1 by n. If you take the velocity v1 as the velocity at the beginning of the interval, right, this will be the calculation. No, you could put that as v0. If you take it as velocity at the end of the interval, it will be v0 plus a delta t. So this can be v0, velocity at the beginning of the interval, which will be this calculation. Otherwise, it could be v1 could be v0 plus a delta t, where v0 is the velocity at the beginning of the interval, first interval. So if you do that, well, if you substitute for v0 plus a delta t and work it out, you'll get v1 v0 t plus a t squared 1 minus 1 by n. If it is v0, so you are getting this answer. S is equal to v0 t plus a t squared by 2 into 1. Do the calculation and you'll find that is by substituting v1 as v0. Do one calculation. This is what you get. v1 as v0 plus a delta t, and you'll get plus 1 by n. So this is 1 plus or minus 1 by n, depending on whether you substitute v1 as v0 or v0 plus a delta t. Now you can see the fun here. You can tend n to infinity, and when you tend n to infinity, this part becomes 0, and you get s is equal to v0 t plus half a t squared. That will be your calculation. And this tending to n is equal to infinity and doing the summation of large number of small terms, that's what we call integration. And it's denoted like this: S is equal to integral of, this special summation is called integration, this sum to infinite number of terms, large number of undefined number of terms, from t equals t1, say 10 seconds, to 20. This is the calculation. Now in our case v is 80, right? If you take t is equal to 0 as the time at the beginning of when it starts moving, this will be v is equal to 80, and this will be 10 and this will be 20. So this is at dt t1 to t2, and this, well, there is an interesting way of doing this. A comes out, and this t dt, well, this t is the part which you are interested in, and that, well, you ask a mathematician and he says, well, he calls the process integration, and to get to the result you got to find out what you should differentiate to get t, and that is t squared by 2. There is an interesting relation between integration and differentiation. So what should I differentiate to get t? T squared by 2, and then these limits t1 and t2. A, of course, a comes out, that's not a variable, so t is the variable here, and this will give us a by 2 into t2 squared minus t1 squared. This a is 1 for us. T2 squared, 20 squared, 400. T1 squared, 10 squared, 100. This is 300 by 2, so 150 meter. Actually it is 150 plus or minus something, but that's something we can reduce it to something so small that we'll just not mention it. This n tends to infinity, and this is the calculation. So this is a specialized summation. Yes, the symbol S for integration, summing up, special kind of summing up of large number of very small terms. So this is how you take care of the variation. Instead of treating the variation as a continuous variation, we'll take it as a stepwise variation and make the steps very, very, very small, and that gives you an accurate result. To remember, when you say the mass of a body is 2 kg, you don't mean this equality in the usual sense of equality. This will be 2 kg plus or minus 1 gram. I mean, the accuracy of the instrument determines whether it's plus or minus 1 gram or 10 gram. So when you say equal to, you mean it can be approximated to 2 kg with a certain error involved in the measurement. So that's the same case with physical quantities. We're calculating displacement, and we do know that physical quantities cannot be the values. They have to be approximated to the accuracy you desire, right? So that's it. Well, say when you buy some sugar, say a kilogram of sugar, and if somebody is weighing it, after the weight is scale shows 2 kg, if it takes a grain away or adds a grain, it doesn't change the reading because that instrument is not sensitive enough. So when you say something is equal, it's so nearly equal that we'll take it as equal. That's it.